Welcome to the Discrete Universe podcast. Today we're diving deep into a really fascinating area where cutting-edge physics meets let's say, the tough scrutiny of the scientific process. We're talking about the peer review of quantum geometry dynamics, or QGD. Now, if you've got a background in physics, you know peer review is basically the crucible where new theories get tested, seriously tested. But what happens when a theory challenges, well, the very foundations of how we understand space-time reality itself? That's what we're here to explore today, the unique hurdles in critically evaluating a framework as radical as QGD, drawing from the concepts and potential limitations highlighted in our materials.
It's definitely a crucial conversation to have because when a new framework like this emerges, especially one aiming to redefine things as fundamental as space and time, the whole peer review process gets incredibly complex. We're not just looking at small tweaks here, it's potentially a whole paradigm shift.
Okay, so let's try and unpack this. The first big challenge seems to be QGD's fundamental departure from, well, established physics frameworks. The source material, that QGD book, lays out this idea of a discrete quantum geometrical space, like space is made of tiny, indivisible units. Now, our current understanding, mostly from relativity, sees space-time as continuous, smooth. This switch to discrete space, it has some pretty profound implications, doesn't it?
Oh, absolutely. Profound is the right word. The second you propose a fundamental unit of length, you immediately run into friction with the principle of relativity, which is, a cornerstone of special relativity. Special relativity is just incredibly successful at predicting how measurements change between observers moving relative to each other. It deals with relative measurements. QGD, though, with its discrete space, it's trying to predict absolute measurements. The idea being that certain fundamental properties would actually have the same value for everyone, no matter how they're moving.
And here's where it gets really interesting. Our sources point out that special relativity, despite all its success with relative measurements, it doesn't really have the tools to handle a discrete space or, predict how physics would work in such a space. And as Ethan Siegel has often emphasized, any new theory aiming to replace established ones faces this massive task. It absolutely has to explain everything the old theories already do.
That's such a critical point, a huge one. Just replicating the sheer volume of experimental evidence backing relativity, but doing it from such a fundamentally different starting point. That's an enormous challenge for QGD. And also, the way QGD is constructed is different too. It's built on this self-consistent set of axioms, with the discreteness of space being like a core non-negotiable principle.
Right, that axiomatic approach. So QGD brings in these core ideas like a principle of strict causality, suggesting every state of the universe is uniquely determined by the one just before it. No wiggle room. It also defines fundamental parts of reality as invariant properties. Now, this is quite different from the usual empirical, kind of deconstructive approach that's dominated physics historically, right? Where we observe, experiment, then build theories. The book suggests that, yeah, the empirical method has been great for understanding what we can see and measure, but maybe not so great at getting to the truly fundamental nature of reality itself.
Exactly. The empirical method tends to work from the ground up, based on observations. An axiomatic approach starts with those foundational principles, the axioms, and then deduces the consequences. So during peer review, a massive question becomes, how do we reconcile these fundamental assumptions, these axioms of QGD, with the well-established principles of existing theories, which were mostly derived empirically? Ideally, physical axioms should sort of fit together or at least be complementary. They shouldn't contradict each other.
Okay, let's shift gears a bit to how QGD actually pictures reality, space, and time. This is where it gets really radical. QGD proposes that space itself emerges from repulsive forces between these fundamental things called preons, and matter comes from attractive forces between other ones, preons plus old. That is a very different picture from the smooth, continuous space-time we usually think about.
It really is a significant departure, yeah. This view directly challenges the mathematical continuum, the whole idea of infinitely divisible space, which, interestingly, even someone like Roger Penrose questioned, calling it potentially foreign to physics, especially that idea of infinite points crammed into any volume. QGD is essentially saying, look, continuous math is a fantastic tool, incredibly useful for approximating reality at larger scales, but maybe it's just not the right language for the fundamental level.
And then there's time in QGD, which it describes as non-physical. So according to this framework, clocks aren't actually measuring time as some fundamental dimension. Instead, they're just counting recurrent states like clicks or cycles within the system. This is just a monumental shift from our standard view, where space and time are the fundamental coordinates of the universe. I can only imagine the kind of intense scrutiny that idea faces in peer review. given how absolutely central space and time are to, well, all of physics.
Precisely. Space and time are woven so deeply into the fabric of all our current physical theories. So any framework proposing such a fundamental reinterpretation, it faces a really steep climb. Peer reviewers would absolutely demand, and rightly so, rigorous justification. A really clear explanation of how this non-physical concept of time can still account for everything we observe about the universe's evolution, causality, the arrow of time, all of it.
Okay, so that leads us to another crucial thing for any new science: testability. Can it make predictions we can actually go out and check? Maybe even prove wrong? The book mentions QGD offers alternative explanations for things we already observe, like maybe gravitational waves are actually electromagnetic effects from this preonic field polarizing. But the real key for acceptance, it seems, is making unique, falsifiable predictions. Predictions that set it apart.
That's exactly right. Spot on. Providing alternative explanations for known stuff is, interesting. It can offer new perspectives. But for QGD to really gain traction, it needs to do more than just reinterpret the existing playbook. It absolutely needs to make novel predictions that we can test experimentally. Predictions that would give different results from what our current theories say. The book does mention the possibility of absolute measurements of physical properties. That could be one area where QGD might diverge from relativity's focus on relative measurements that could potentially offer a way to test the two frameworks against each other.
There was that example in the book, too, about gravity, non-delayed versus time-delayed gravity, predicting slightly different angles for light deflection near a massive object. And QGD's prediction apparently aligns with general relativity on that one. So that seems like a testable aspect, right? Even if it agrees in that case?
It is a testable aspect, yeah. And agreeing with established theories, as Siegel pointed out, that's a necessary first step. You have to reproduce the successes. But the real power, the real proof of a new theory comes when it makes predictions that diverge, and those can be tested. If QGD could predict something that contradicts GR or the standard model, and then an experiment confirmed QGD's prediction, well, that would be incredibly strong evidence for it. The discussion in the book around the one-way speed of light is another area where QGD's implications might potentially differ from conventional interpretations.
This kind of brings us to the more philosophical side of things. QGD's fundamental assumptions about reality, moving away from continuous math. These have deep philosophical implications. And then there's Occam's razor, the principle that often guides us towards simpler explanations. So how does a theory like QGD fare when you apply Occam's razor? It seems to introduce new things like preons and discrete space. Does that make it less simple?
Applying Occam's razor here needs careful thought. It's not always straightforward. The question is, are QGD's fundamental postulates, these preons, the discrete space, are they truly necessary assumptions? Do these new assumptions ultimately lead to a more economical, a more comprehensive understanding of the universe, even if they seem less intuitive initially? It's not just about counting assumptions, It's about whether those assumptions are well justified and whether they lead to a more coherent and crucially predictive framework overall.
Yeah, and the online discussions we looked at brought up a good point, too. Occam's razor isn't necessarily about which theory looks simpler conceptually. It's more about avoiding unnecessary assumptions. So a theory that makes fewer established assumptions, like maybe challenging relativity, might actually be seen as less parsimonious if its own core postulates, the new ones, are really complex or don't have strong independent reasons behind them. It's nuanced.
It is very nuanced. The critical question is whether introducing these new fundamental concepts, this whole new axiomatic structure, does it ultimately give us a more streamlined, more complete picture of reality? And as was also pointed out in those discussions, the universe itself might just be inherently complex. Sometimes our drive for elegant, simple explanations might actually cause us to overlook that underlying complexity. A theory that maybe grapples with that complexity, even if it needs more initial postulates, might in the end be a more accurate reflection of how things really are.
Which leads us, finally, to maybe the most human part of this: community acceptance and paradigm shifts in science. Introducing a theory that challenges such fundamental principles, well, it often meets resistance. It's almost expected. Max Planck's famous observation comes to mind, right? That new scientific ideas often only win out when the older generation, attached to the old views, passes away, and the younger generation grows up learning the new concepts. It really highlights this.
Planck's quote, absolutely underscores that sociological dimension of scientific progress. It's not just about the data. And the history of physics is just full of examples of groundbreaking theories that were initially met with skepticism, sometimes even outright rejection. Think about quantum mechanics itself in the early days. Peer review, while it's absolutely essential for rigor, for filtering out flawed ideas, it can also, sometimes inadvertently, create hurdles for radically new concepts, especially ones questioning those deeply ingrained assumptions about reality.
And you have to consider the strong consensus around incredibly successful theories like relativity and quantum mechanics. That consensus creates a very, very high bar for any alternative framework like QGD to clear during peer review. It demands not just compelling theory and testable predictions, but also a significant shift in how the whole physics community understands and accepts things.
Precisely. It really is a delicate balance. You need the rigor of the scientific process, absolutely. But you also need to foster an environment where truly revolutionary ideas can at least get serious consideration. Evaluating a theory as fundamental, as unconventional as QGD, requires more than just deep technical knowledge. It requires an open mind, a willingness to question long-held beliefs, and maybe contemplate entirely new ways of picturing the universe.
Well, it's certainly a lot to think about. For those interested in really digging into the details of QGD itself, I would encourage you to read Burstein's book titled Quantum Geometry Dynamics, An Axiomatic Approach to Physics. Thank you for listening to the Discrete Universe podcast.